Welcome back to The Explainer. Today, we're unpacking an absolutely fascinating framework called Macbeth. We're going to dive right in and uncover exactly how you can take complex, completely contradictory human feelings and somehow, miraculously, translate them into rigorous, quantitative scores. Let's get into it. So, think about this for a second. How do you mathematically model subjective human preference? It's literally one of the toughest challenges in operational research. When we're faced with multiple conflicting criteria, our brains naturally hold contradictory views. It makes it notoriously difficult to pin down exactly how much more we prefer one option over another. It's a massive headache that researchers, executives, and data scientists wrestle with every single day. Now, you might be thinking, hey, why not just use a simple weighted sum? Well, a basic weighted sum completely fails us here because it assumes our preferences are perfectly linear. And let's be real, human utility rarely works that way. Think about salary, for example. Depending on your personal financial situation, earning £4,000 isn't just twice as good as £2,000. It might actually improve your real-world utility by a factor of 5. This nonlinear reality is exactly why we need a specialized framework to capture the true weight of our choices. Okay, here's our roadmap for today. We'll hit 1. The complex decision problem. 2. Introducing the Macbeth method. 3. Structuring the value tree. 4. Semantic judgments and inconsistencies. And finally, 5. Inside the black box. Section 1. The complex decision problem. The entire field of multi-criteria decision analysis, or MCDA, exists for situations precisely where simple math falls apart. Because an absolute, perfect, ideal option almost never exists across all your criteria, right? A compromise is always required. Unlike those fully automated black box models that spit out the exact same robotic answer for everyone, MCDA actually places you, the decision maker, and all your subjective constraints right at the center of the process to find a truly tailored compromise. Section 2. Introducing the Macbeth method. Macbeth. It stands for Measuring Attractiveness by a Categorical-Based Evaluation Technique. It's a bit of a mouthful, I know, but it is a premier qualitative to quantitative tool. It's designed specifically to take your categorical qualitative feelings and lock them into a definitive, mathematically sound measure of attractiveness. If you've spent any time in this space, you probably know Macbeth's famous cousin, the analytic hierarchy process, or AHP. Both rely really heavily on pairwise comparisons, so they look kind of similar at first glance. But here is the absolute game changer. AHP uses a ratio scale, while Macbeth uniquely operates on an interval scale. And this exact mathematical distinction is what allows Macbeth to translate your everyday qualitative semantic judgments directly into ranked, robust numerical data. To actually pull off the Macbeth framework, you've basically got to complete 3 distinct steps. First, structuring the problem, setting the boundaries of the decision. Second, entering pairwise semantic comparisons to measure attractiveness. And third, checking for any logical incompatibilities in your own human judgment. Section 3. Structuring the value tree. Let's make this concrete. Imagine you're organizing a 3-day university conference. You have a brutal schedule, an uncertain headcount of around 200 people, and you desperately need to pick a caterer. Now, anyone who's ever run one of these committees knows that a delayed lunch will literally derail the entire afternoon. You're down to 4 compromise options: an internal university caterer, a Japanese caterer, an Indian caterer, or a Chinese caterer. To tackle this, we have to build what's called a value tree. You take the overarching caterer selection and split it out into core criteria: quality, price, reliability, and flexibility. Then you break quality down even further into things like consumables, the actual food and drinks, and service. By mapping out the decision visually like this, we're forcing some much-needed, rigorous structure onto the usual chaos of committee decision-making. Section 4. Semantic judgments and inconsistencies. This right here is where Macbeth truly shines. Instead of forcing you to pull arbitrary numbers out of thin air, you simply compare options pairwise using 7 semantic categories. These range from no difference all the way up to extreme. You're answering entirely in natural language. You literally just say, option A is moderately more attractive than option B. It is incredibly intuitive and vastly lowers the cognitive load on whoever is making the decision. So you'd pull up a matrix for a specific criterion, let's say quality, and fill in the grid using those exact semantic words. For instance, you might note that the Japanese caterer is extremely more attractive than the Chinese caterer, but maybe only very weakly more attractive than the Indian caterer. The model relies entirely on these qualitative human inputs to populate itself. Now, here's where the magic happens. The software immediately takes all those qualitative words and mathematically translates them into a quantitative thermometer scale. It generates a strict interval scale anchored with a high of 100 and a low of 0. So, based entirely on those everyday semantic words, the Japanese caterer suddenly scores a perfect 100 on quality, the Indian caterer lands at 85.7, the internal caterer drops to 14.3, and the Chinese caterer scores a 0. But humans are inherently contradictory, right? We mess up. So the software actually acts as a strict mathematical guardrail checking for two distinct errors. The first is incoherence. This is a literal logical loop where you say A is better than B is better than C, but then somehow C is better than A. The second is semantic inconsistency. This happens when the magnitude of your qualitative jumps doesn't mathematically align. For example, if the gap between A and B is weak, and B and C is weak, but then you claim the gap between A and C is extreme, well, the underlying math simply won't support that massive leap. Section 5. Inside the black box. Behind the scenes, Macbeth is powered by a linear programming engine called LP Macbeth. This engine sets up an objective function specifically designed to minimize the score of the most attractive option. It rapidly runs through a massive list of semantic conditions, strictly enforcing your qualitative constraints, so no logical rules are broken. If it does find an inconsistency, the software literally forces you to revise your judgment before moving on. Finally, it normalizes the whole shebang to that commensurable 0 to 100 interval scale, allowing totally divergent criteria, like price and quality, to be accurately weighed against each other. And all this leaves us with a pretty profound question regarding decision theory. If human preference is inherently messy and inconsistent by nature, and the Macbeth software essentially forces you to resolve your natural contradictions to satisfy its linear programming, well, does the final ranking truly reflect your complex preference? Or does it merely reflect the algorithm's unyielding logic? It is definitely something to chew on the next time you're faced with a high-stakes choice. Thanks so much for joining me for this explainer, and as always, keep questioning the data.